All right, finally, moving on from chemical kinetics, we're getting into chemical equilibrium. We've got a nice little quote up here from our friend Henri Le Chatelier. You may remember his name from Chem 3A. He had a particular principle, which I'm sure we'll get to at some point. So we've been talking about kinetics, and kinetics determines the speed of a reaction. Not all reactions will go entirely to completion, particularly reactions that are reversible. So reversible reactions, the extent, how far they proceed, is governed by thermodynamics, and that's some of the stuff we'll be talking about today. So what balance of reactants and products do we have? And our equilibrium constant K is an experimentally measurable quantity that we can use to actually put a number to where that balance lies between products and reactants. You hopefully remember a little bit about the equilibrium constant, but some key points are that if we have a large K, a large equilibrium constant, the reaction is going to favor products. So we will have more product than reactant. And the opposite is true if we have a small K. And small and large here are referring to things that are much, much larger than 1 and much, much smaller than 1. So like 10 to the 19 would be a large K, and a small k might be 10 to the minus 6 or smaller. And we'll talk about some other things relating to that in a couple chapters. One example of a place where equilibrium plays a role in our bodies is hemoglobin. So you may know that your body has red blood cells, and you've got a protein called hemoglobin in there that reacts with oxygen. It'll pick up oxygen like in your lungs and then dump it out wherever it needs to go in your body. We've got this double-headed arrow, meaning that it's reversible. So we can have the hemoglobin picking up the oxygen to form oxygenated hemoglobin, and we can also have the oxygenated hemoglobin dumping off its oxygen, depending on the conditions that it's in. And if we have a system that can establish an equilibrium, it's going to respond to changes. We'll often talk about that shift left or right. So creating more reactant, shifting to the left, creating more product, shifting to the right, in an attempt to maintain or reestablish equilibrium. So in your lungs, hemoglobin has access to oxygen. So in your lungs, you're going to have a high oxygen concentration. In order to try to establish an equilibrium in this reaction, because of all this oxygen, hemoglobin is going to be picking up that oxygen to turn it into oxygenated hemoglobin. This sort of is Le Chatelier's principle. So we're having a high concentration of oxygen, so we're going to cause that reaction to shift right and produce HBO2. Which is good. And then that oxygenated hemoglobin, and some that's not, I'm sure, will get circulated around your body, and it'll find places like muscles, other parts of your body, that have low hemoglobin, or low oxygen, sorry. and it will shift left. Not shift left. And release oxygen into your muscles and cells. This also works for fetuses. So if you have a small human being growing inside you, developing inside of you, they're connected with the umbilical cord, and they need to get oxygen as well. Obviously, they can't breathe oxygen because they're, breathing embryonic fluid. And so there has to be an exchange of oxygen between the parent and the fetus. And that occurs through intricate blood stuff. You don't need to know any of the biology about this. This is just an instance of, hey, here's another cool application of this. So it turns out fetal hemoglobin has a large K. And remember that the oxygenated form is on the right side. So that's going to be big at equilibrium. Lots of that at equilibrium. It's bigger than the K for our hemoglobin. And so it's going to take oxygen from the parent and be able to deliver that throughout the rest of the fetus. Which is neat. Another thing, while we're talking about hemoglobin, you may know that carbon monoxide is bad for you. Carbon monoxide is bad for you. Part of the reason for that is that we've got this oxygen end of carbon monoxide that to hemoglobin looks an awful lot like O2. Right, very similar. And hemoglobin is used to this bond length and strength of the oxygen. So when it bonds to the oxygen in carbon monoxide, that's actually a stronger bond, and it's harder for it to release the carbon monoxide. And so it basically takes up space in your hemoglobin until it can release it after a longer period of time than it takes for you to release oxygen. And that's why, part of why carbon monoxide is so dangerous. It basically stops your body from being able to take in as much oxygen. So that's neat. Okay, about dynamic equilibriums. Reaction rates, as we know, generally increase with increasing reactant concentration. And we have reversible reactions that can work in both directions. As our reactants react, we use up some of our reactants, of course, and the rate of reaction is going to slow down, and slow down, and slow down, until it eventually reaches a point where it's in competition with the reverse reaction. I'm sure that I could have made a very cool graphic that shows you what's going on, right? But basically our reactant side, we've got a lot of reactant, our product side. As our reactant starts to decrease, we're increasing our products, and those will start to go back to form reactants, and they find a balance at some point until they eventually find the right concentration at which the rates are equal back and forth, and then they stop changing concentrations. Here's a couple of ways that we could look at that. So we've got time up on the top, just in case you weren't sure that we were moving forward through time from left to right. Initially, we've got hydrogens, and that's also a hydrogen. This is an iodine, and those will react to form HI. So we can see after a little bit of time, we've got 4 of those created. After a little bit longer, we've got more of those created. And there's no change between our C and D. in the amounts that we have. And so that indicates that we've reached dynamic equilibrium. We can also represent it with concentrations as our y-axis on a graph with time as our x-axis. So initially we've got high concentrations of our two reactants, and those are going to decrease over time as we produce our product. So our product concentration comes up, and they start to slow down as they reach equilibrium. And then once we've established dynamic equilibrium, there's no change in our concentrations. And by no change, like there's still things moving back and forth, right? 'Cause that's the dynamic part. Still things going in both directions, but the overall concentrations at the observable level have not changed and won't change. And here's our definition, bolded. And I'm going to box it in too. Dynamic equilibrium is the condition when the forward and reverse rates are equal. Again, the important thing is that the rates are equal. It's very common for people to get confused, especially in 3A, and think that the concentrations are equal, which is not the case. The concentrations could be equal, but in only very, very limited cases, and so we're going to just go ahead and say that they're not equal, because that would be the exception, not the rule. So we are going to have different concentrations, except in very particular circumstances that probably won't come up. Another analogy for dynamic equilibrium is if we have two countries. In 3A, the analogy uses mythical lands like Narnia and what's the name of the Middle Earth? I was going to say Mordor, but that's not correct. So if we've got country A and country B, let's say that country A has been around for a while and country B just poof came out of nowhere and there weren't people living there already, or maybe they were, whatever. So country A, we've got a ton of people, too many people arguably, but we've just discovered that there's a brand new country B that's been right next to us this whole time, and we just couldn't see it. Wow, that's a lot of free real estate. So obviously people are going to move in. It's free real estate. So we get a bunch of people emigrating from country A to country B. At some point, assuming that like country conditions don't change, some of the people that are in country B will be like, hey, I actually liked living in country A better, and now there's a lot of people in country B. I'm going to just go ahead and go on back to country A. At the same time, there's going to be people thinking the same thing, but not exactly the same thing because they've never been to country B. Be like, hey, I really like the way that country B looks. The grass sure is green over there. And then they'll move over to country B. And assuming that country conditions don't change, you would expect to see roughly equal rates of change across those two country borders. Country A might be 50 times the size of country B. There might be a lot more people in country A, but because of the way that things are, you get equal rates of immigration, possibly. Free real estate. All right, testing our knowledge of dynamic equilibrium. Which statement does not generally apply to a chemical reaction in dynamic equilibrium? the rates are equal, the concentrations are constant, the concentrations are equal. Yes, it is C. Questions so far? This has mostly been review. All right. Our equilibrium constant K, we define it this way. So our equilibrium constant is a nice way of defining our balance of reactants and products. You should have this general scheme of how to come up with an equilibrium constant memorized. For me, the big part wasn't remembering that we're raising the concentrations to the coefficients. It was remembering which side is on top, products or reactants. I always got that mixed up when I was learning it. It's products over reactants. So products over reactants. That's my equilibrium constant mantra. So for our generic equation, our concentration of our first product raised to its coefficient as the power times concentration of our other product raised to the coefficient of its power, or whatever. And the same thing for A and B, but on the bottom. And these are molar concentrations. And in the slides, K, just standing up, normal K, is going to be our abbreviation for Kelvin. And K, just slightly slanted, is our equilibrium constant. So if it's in italics, we're talking about the equilibrium constant. So most of the time it'll be that one. According to the law of mass action, that's this thing. According to that, what is the correct expression for the reaction 2A plus B in equilibrium with 3C? We've got a guess for D. Why is it D and not C?
Because the products go on top.
Yeah, products over reactants. So we've got C raised to the 3, because that's its coefficient. We've got a 2 in front of our A, so our concentration of A is raised to the second power. We also have concentration of B in the denominator. Products over reactants. Here's another example of the law of mass action. It is important, perhaps, to note that this has to be for a balanced chemical equation. It would be a little bit devious to give you an unbalanced chemical equation. But again, my general rule for chemical equations, if somebody's giving you a chemical equation and there's coefficients, it's probably balanced. It's always worth checking, I guess, if you want to. If there's no coefficients, it's probably worth checking. All right, go ahead and write the equilibrium constant for the combustion of propane as given in the balanced chemical equation here. I'll give you a minute to work on that. All right, we have to use the law of mass action, our formula for coming up with a K, an equilibrium constant. What did we come up with? You can omit the concentration part.
CO2 to the third power.
Yeah,
H2 to the fourth power.
great.
On the bottom, C3H8.
Great.
And then O2 to the fifth power.
Perfect. So we've got our products on top. We've got our coefficients turning into exponents. And everyone is represented. So that would be a great equilibrium constant expression. The equilibrium constant, as mentioned earlier, when K is large, much, much larger than 1, that means that our numerator is larger. And we know that K is products over reactants. So when our numerator is larger, that's the products. When our denominator is the reactants. And so the forward reaction, the reaction that produces products, is going to be favored. If we have a small k, then the reverse reaction is favored. Products are not stable, possibly. And we're going to have more reactants than products at equilibrium. The equilibrium constant, however, doesn't say anything about the speed, the rate of the reaction. It just tells us where it will land up eventually, given enough time. Here's a summary slide in case you need to review. Consider the reaction A in equilibrium with B. The images shown here illustrate equilibrium mixtures at different temperatures. At which temperature is the equilibrium constant the largest? A is red, B is black.
C.
Yes, it is C. It's C because we've got the most product. We have, how many do we have? 1, 2, 3, 4, 5, 6, 7, 8. 8 product, 2 reactant. Assuming that these are representative, our KEQ is 4, not very big. But that's still the biggest ratio. In these other ones, we've got 5 and 5, like in B. And in A, we've got 4 products and 6 reactants. So the one with the most product is going to be the one that has the largest equilibrium constant. If the equilibrium constant for the same reaction is 10, and a reaction mixture initially contains a concentration of A that's 1.1 molar, and the concentration of B is 0.1 molar, which of these statements is true at equilibrium? We've got a guess for B. Any other guessers? All right, our guess for B. Our equilibrium constant is equal to 10. So 10 as our equilibrium constant is equal to the concentration of B over the concentration of A. If we wanted to, we could rearrange this. We would find out B equals 10 times the concentration of A. And in B, little b, our concentration of B is 10 times our concentration of A. That meets our description for our equilibrium constant, so that's the correct choice. Questions? All right. If you thought that was fun, there's more fun to be had. If we change our chemical equation, which we can do, our equilibrium constant also changes because of the way that we changed it. These are all rules that you could probably come up with on your own. We're just learning 3 rules. The first is if you reverse the reaction, you invert the equilibrium constant. You swap the top and bottom. That's because our reactants and our products are changing places. It's always reactants over products. So if we swap our reactants and our products, that flips or inverts our equilibrium constant. So for example, in this left example, the forward direction, we've got the concentration of C raised to the 3rd power over the concentration of A times the concentration of B squared. That's what our equilibrium constant would be. In our right example, which we're calling K reverse, our equilibrium expression is concentration of A times concentration of B raised to the 2nd power over the concentration of C raised to the 3rd power. This is just to show you that when we switch our equation, we're flipping the top and bottom. So if our KEQ, as I'm used to calling it, was 5 for our left reaction, our equilibrium constant expression has flipped. It's inverted when we switched sides. So we invert the 5, and our equilibrium constant would be 1 over 5 for the other example. One of the reasons this is nice is because if we've got numbers for our equilibrium constant, we can change up our equation or combine equations together, as we'll see later, and we can just work directly with the numbers. We don't have to necessarily think through all the steps or write everything out and plug a bunch of numbers in and all that stuff. If we multiply the coefficients by a factor, that means that we raise the equilibrium constant to the same factor. So again, we've got concentration of C raised to the 3rd power over the concentration of A times the concentration of B squared. And then we've multiplied our coefficients by some factor and just standing in for any number. So in this new scenario, our coefficients are concentration of C raised to the 3rd power, where that 3 is multiplied by n, over concentration of A raised to the n power, concentration of B raised to the 2n power. So we can pull all of those out. And this term on the inside here, all the stuff that's in green, that's our original K. So we've taken our K value and raised it to the n power. Voila, math. You don't need to know how to derive these, but the derivation is helpful for some people. So if our K initially was, let's say it's 5 again, and let's say that our n is 3, right, so that our coefficients are 3, 6, 9, then our KEQ for this new setup would be, I've swapped my colors, 5 raised to the 3rd power. So it would be 125. All right, 2 rules down, 1 to go. If you add 2 or more chemical equations to obtain an overall reaction, multiply the corresponding equilibrium constants to obtain the overall equilibrium constant. So we're combining these 2 reactions together. So we would expect that those B's cancel out since they're an intermediate, and so our overall chemical reaction would be A in equilibrium with 3C. And we would expect for this equilibrium constant, we'll call it K3, my younger brother, to be concentration of C raised to the 3rd power over concentration of A. If we take a look at K1 and K2, my older brother and me, if we multiply those together, pick some colors for these, concentration of B squared over concentration of A times concentration of C cubed over the concentration of B squared. We can see that the B squareds canceled out. And we get back K2. So K1 times K2 equals K3, our new equilibrium constant. Questions about our very fun rules that we've just learned?
And is adding the subscripts the same as adding like exponents? Like when you multiply them, you're just adding them?
Oh no, the subscripts are arbitrary. For the K1, K2, K3.
Yeah.
Yeah, those are arbitrary.
Okay.
I just saw a trend, so I thought, let's call it K3.
Okay.
We could have called it KX if we wanted to, or K phi if we were feeling spicy. All right, let's use some of those rules. We've got the reaction A in equilibrium with 2B. it has an equilibrium constant of K equals 0.010. What is the equilibrium constant for B in equilibrium with 1/2 A? So we're doing two things. Think through what two things we're doing and how those affect it. All right, so our two steps, we've got A in equilibrium with 2B to start, and we're trying to turn that into B on the left side with 1/2 A on the right side. There's two steps that we'll need to take to do that. One of them is flipping it left and right, so we'll do that first. That's going to be our intermediate step. So we flip left, right, and then divide coefficients by 2. So when we flip left and right, we have to invert it because we've swapped now the position of our reactants and our products. So that's going to cause our reactants and our products to flip for our KEQ, or K expression, equilibrium expression. So starting with 0.010, when we invert that, we end up with 100. And then we divide our coefficients by 2, and since our coefficients are exponents, we're going to divide our exponents by 2. And when we divide an exponent by 2, that's a square root. So we're applying a square root to each of our coefficients in our KEQ, or equilibrium expression constant expression. And so that's going to transfer out to taking the square root of our K. So we should end up with 10 for our equilibrium constant. If you do the steps in the other direction, you should get the same answer, or in the other order, rather. So B. Questions? Yes?
How do you invert it? Like, how do you get from 0.0?
That's 1 over 0.010. Does that answer your question? Okay, cool. You can also raise it to the -1 power. That would be the same thing. All right, consider the following chemical equation and equilibrium constant at 25 degrees C. Calculate the equilibrium constant for the following reaction at 25 degrees C. So we've switched things up. We want to calculate what the equilibrium constant is going to be. Still at the same temperature, which is important. So think through what steps we need to do and how those are going to affect our K. All right, we've got 2 steps. How about we just say, let's start saying we've got some steps. One thing that we can do is we see that we've got CO2 and CF4 on the right side in our original. Those are now our reactants instead of our products. So we flipped it left and right. So we're going to invert K. The other thing that we've done is we've multiplied all of our coefficients by 2. And so we're going to raise K, our new intermediate K, to the, let's just say we're going to square K. How about that? So we're going to do both of those things. So our new K would be K raised to the minus 2 power, or 1 over 2K. Sorry, K2. So in the calculator, 1 divided by 2.2 E6 to the 2nd power. So like that. And in my calculator, I'm getting out 2 let's round it up to 1, times 10 to the minus 13. Since we're squaring this 6 in our denominator, this exponent 6, these exponents multiply, the 6 and the 2. So 1 over 2.2 times 10 to the 12-ish, and it's negative, and I maybe put something in wrong, but we're in the right ballpark. Questions? We can also do other stuff. For example, we want to predict the equilibrium constant for this first reaction. So we need to set up this first reaction using our other 2 reactions. I'm looking at the H2 as something to focus on here. Our second reaction, that's this bottom one, our bottom reaction already has 2H2 on the left side, so I think we should keep that. In the way that it is. Our second reaction also has H2, but it's on the product side. We don't want that. We want it on the other side. So copying this one down, and our other one we're going to flip left and right. So we'll have CO2 plus H2, double-headed arrow, CO plus H2O. The idea being that when we add these H2s up, we'll have 3 H2s. So let's cancel stuff out. We've got carbon monoxide on both sides, so we can cancel those. And I did not use my space particularly wisely. Classic. So CO2 plus 3H2 with our methanol and our H2O. So this is the equation that we want. So we've set these up correctly. The only one that we have to change is the one that we swapped the CO2 left and right. So the one that we inverted, we'll have to change K2 So we'll call that K minus 2 is 1 over 1.0 times 10 to the 5. We flipped it left and right, so we invert our K value. We didn't change the bottom reaction, so that's still K3. And then when we combine the reactions, what does that mean we do with our K values? Yeah, we multiply them. So K1 is going to be 1.4 times 10 to the 7 over 1.0 times 10 to the 5. We should end up with something that's roughly 10 to the 2. 1.4 times 10 to the 2, I think. Yeah, 140. So that's some of our fun rules in action.
Are you dividing them because the K negative 2 goes to the top, or how did that work?
So the K minus 2, it's 1 over 1 times 10 to the 5.
Okay.
There's the 1. I just ignored the 1 part and then combined them because I did a me and I ran out of space.
So if it was K subscript positive 2, then you would multiply them, like just straight across and not divide?
Yeah, it's K minus 2 because we flipped the
Yeah. Okay.
flipped the script. Another fun thing that we can do that we haven't done yet is express K in terms of pressure. So when we're working with things that are roughly ideal, we can do this. For gaseous reactions, the partial pressure of a gas is proportional to its concentration. And our expression for Kp takes the same form, except that we use partial pressure instead of concentrations. So for the same reaction, our Kc, concentration of SO2 raised to the second, instead of that we have partial pressure of SO2 raised to the second power. For concentration of O2, we've got PO2, and for concentration of SO3 squared, we've got partial pressure of SO3 squared. Kp is our equilibrium constant with respect to pressure. Atmospheres is assumed here. That's our reference state. So we've got Kc, concentration, and Kp, our equilibrium constant for pressure. And you might think to yourself, what a wonderful world. You might also think to yourself, well, aren't those two kind of just the same thing? And it turns out that they are not just the same thing. Let me remind myself, okay, great, I did write it all out. We'll just leave that there then. So the value of Kc is not necessarily equal to the value of Kp, but they're related to each other and we can convert them. So the partial pressure of a gas in atmospheres is not going to be the same as its concentration and molarity, but we can relate the two assuming that it's ideal. Which we're usually going to do because this is a classroom and it's also an undergraduate class. We're not going to get that complicated. So we want to relate molarity and pressure. Hopefully, what comes to mind is PV equals nRT. Our molarity, moles over liters. Our symbols would be N over V. And our partial pressure just being P for pressure. So we want to relate N over V and P. We can do that by rearranging. So P equals nRT over V. That would be one way of doing it. We could also instead put the RT on the other side. So that might look like this. So there's our relationship between the two. And we can do the very fun thing that we're going to be doing here, using that concentration is equal to P sub A, the partial pressure of A over RT. We can do this whole mess of stuff. So what we're doing here, we're starting off with our Kc. So we write out our generic equation for that. Right, concentration of A raised to the subscript of A. Then we swap in concentrations, P with the subscript for whatever the thing is, over RT. So substitute all those in. We've got this real big mess of equations. And then what we can do is pull out all of the RTs. So we distribute our exponents. We get all of our partial pressures together, the RTs all get pulled out and set aside. And then if we want to, we can also combine the exponents. And since this whole bit here is just equal to Kp, we can sum that up as Kp. And I wrote the subscripts wrong down here. No, I didn't. I wrote those correctly. So Kc is equal to Kp times RT raised to the C plus D minus A plus B. Basically just the difference in the coefficients. And we can flip it. We can flip the order of the exponents. So do A plus B minus C plus D to get Kp by itself and Kc on the other side. The A plus B, C plus D part, I think, is not going to be important for us. Questions about coming up with any of that madness?
So how do you get the last part? Like when you go from like what's circled in green to the part to the right of that?
These two things are multiplied by each other. So I pulled out RT raised 1 over RT raised to the A, 1 over RT raised to the B, 1 over RT raised to the C, 1 over RT raised to the D. And then they flipped sides since they were all in the denominator. So the C and the D ones flipped up to the top since they were in the denominator of the denominator. And the ones that were in the denominator of the numerator, the A and the B ones, I put down there. I thought that would be a little bit less crazy than 1 over RT raised to the A, 1 over RT raised to the B. You don't need to know how to do the derivation. This is just so that you know that, like, I didn't just make it up. I can also show you where it came from. So this is probably the more important bit to know. The relationship between the partial pressure form and the concentration form is RT raised to the difference in the number of moles of reactants versus products. If both sides have the same number of moles, then delta N equals 0. And Kp equals Kc. Since RT raised to the 0, like anything else raised to the 0, will be equal to 1. So they are equal in that one specific circumstance. All right, considering this reaction and the Kc value given, what is the value of Kp at this temperature? We know that Kp is Kc RT delta N. This We know what Kc is. We know what R and T are. What is delta N? Delta N is 2. That's the number of moles of gas on our product side, minus 1 and 1, which is also 2. So the difference in the number of moles is 0. And our Kp is the same as our Kc. So it's the 6.2 times 10 to the 2. Questions?
What is the R constant for this one? Is that the 8.314 or is that the 0.0821?
Which one do you think it is?
The 0.0?
It is the 0.08206, yeah. And that's because the RT here is from PV equals nRT. So we need the liters atmospheres per mole Kelvin version of R, which is the 0.08206. When we write out equilibrium constants, they are typically expressed as being unitless. So you just don't have units, it's just a number. Even if there's not an equal number of moles and like it should end up with, some molarity value, it doesn't. So they're relative to a reference of 1 molar or 1 atmosphere. So for example, that 3.7 molar relative to 1 molar, just to get rid of the units. So we would just write 3.7. So as long as you're expressing them in molarity and partial pressure in atmospheres, then you can just drop the units and everyone else should know what you're talking about, or should know what the units are supposed to be for dealing with them. All right, let's see if we can knock out a couple more slides. We've got a generic reaction. In some cases, in a case, Kp and Kc for this reaction are going to be the same. Is that going to be A when A plus B, the lower cases, equals lowercase c plus lowercase d? Is it going to be if the reaction is reversible, or is it going to be if the equilibrium constant is small?
A.
Yeah, it's going to be A, because that this thing. We can see that the reaction is reversible. That has no bearing on that, though. And the equilibrium constant size doesn't matter either. All right. Sometimes we will do reactions that are not homogeneous. They're heterogeneous. So we'll have solids and liquids as well as gases. the concentration of a solid or pure liquid doesn't change. As long as you have some there, the concentration of that thing is constant. Just like in the solid form or the liquid form, it's going to be the same concentration. And so we can just omit concentrations for solids and liquids. What this looks like in practice is we've got the reaction of carbon dioxide dissolving in water, water being a liquid, everything else being gases and AQ. So we can write out our equilibrium constant. It's products H plus and HCO3 minus over reactants, concentration of CO2, and we would write concentration of H2O. We can get rid of that, turn it into a 1. So our actual equilibrium constant expression is the same thing, just without the H2O part. So you might choose to just cross things out so that you remember to ignore them. Questions about that? All right, then that'll do it for the first half, but at least the first third of this chapter.